Okay, so like I said, I'm going to go through the examples on page 146. Okay, exercise 1, part A, is asking us to find the Fourier transform of e to the minus t ut. Okay, so we've got a function in the time domain, which is e to the minus t ut. Remember, ut is this thing called the Heaviside step function. If that's time and this is ut, and we have a point here, 1, ut looks like this. Comes along at 0. When you get to time equals 0, it steps up to 1, and then we'll continue on like this. Okay? So any function that's multiplied by that basically has a value of 0 before time equals 0. So this is a one-sided decaying exponential. Okay? And if I was to plot that, it would look something like this. Although not exactly. This is not to scale. If this is e to the minus t, you get something like that. Okay, but because it's u times by ut, this bit doesn't exist. It's just along, then up to this point, and then down like this. Okay, so this is that function, and we need to find the Fourier transform of this. So let's big F omega, because we've got a little f here. Okay, it's the Fourier transform, which is that funny f symbol. Then we use curly braces, f of t, and obviously we could write out again with the actual function in there. So e to the minus t u t. And what I'll do for this one, I'll just apply the theory, and for the others you'll see that they're very similar, so we won't go through the theory for each of them. But we know that the Fourier transform, okay, the equation in the notes, is single-sided, so we can go from 0 to infinity as the integral of our function, f of t, times by e to the minus j omega t dt. Okay, so that's the equation for the Fourier transform of a time domain signal. And so we can write out, insert the function into there. So we've got e to the minus t times by e to the minus j omega t dt. And the reason I've not put u of t in there is that we're integrating from 0 to infinity, so u of t has been applied. Okay, it's only positive from 0 onwards, so we don't need to integrate the bit from minus infinity to 0 because that's 0. Okay, there's no area under that curve at all. So we apply that. Okay, and obviously we can rewrite this. We can combine those two exponentials into one. So that's what I'm going to do here. That's going to be e to the minus, and then we've got t, and then minus j omega. So we've got a 1 plus j omega, and then that's all multiplied by t dt. Okay. This is relatively straightforward to integrate. It's an exponential, so we end up with the exponential on top as well, and that's exactly the same as it was, 1 plus j omega t, but we have to divide it by the constant that's in front of the exponential. So we have downstairs you've got minus 1 plus j omega, and we integrate between 0 and infinity. When we have infinity in here, we've got e to the minus infinity. Okay, e to the minus infinity is 0. And then when we've got 0 in here, we have 1. Okay, so essentially we're going to have in the front of this, we've got minus 1 divided by minus 1 plus j omega. Obviously the minus signs will cancel, and we end up with 1 divided by 1 plus j omega. So that's the solution. Okay, this is the Fourier transform of e to the minus t ut. And if you remember, in the theory we actually did, so as an aside, okay, we actually did the theory of if we had f of t is e to the minus alpha t ut, we found that the Fourier transform of that was 1 over alpha plus j omega. So if you'd have known that, you could have gone straight to the solution, because obviously in this case alpha is 1, e to the minus t, so alpha must therefore be 1 alpha. So for part B and C, we can actually apply the same logic, same theory, exactly the same way, but with different values of alpha. So part B, we've got f of t is e to the minus 3t ut. So straight away we can say that the Fourier transform of that, f of omega, is going to be 1 divided by 3 plus j omega. Exactly the same theory, just a slightly different number. And C, we've got f of t is e to the minus t upon 2 ut. So here alpha is obviously 1/2, and so we could apply that theory, f of omega 1 over 1 divided by 2 plus j omega. In part D, we've got a slightly different problem. We've been given to find f of t, and f of t is going to be 1 divided by 4, when the absolute value of t is less than or equal to 3, and it's 0 otherwise. Absolute value of t is greater than 3. Okay. So this is quite clearly a rectangular function. If this is the time, and here we've got f of t, we have something that looks a little bit like this, where this is 3, this is minus 3, and the value at this point is 1 divided by 4. Now last week we talked about this rectangular function, and it was denoted by p with a subscript a, okay? And that was defined as 1 between minus a and a, and it was 0 elsewhere. So for this function, obviously we've got 1, this function here must be 1 divided by 4, p, and then a is obviously 3. So that's how we can define that function. Instead of writing it like this, we could actually write it like that. It's the same thing. And we knew that the Fourier transform of this one, big P omega, we found to be 2a sinc omega a, or you could write it as 2 sine omega a divided by omega. It's up to you. But they're equivalent to each other, those things there. Now what I'm going to do is I'm going to match up this solution with the solution that we plan on having. Okay. Here we've got a equals 3, amplitude is 1/4. Yeah, with this function the amplitude is 1, okay, because there's 1 there. But here we've got the amplitude being 1/4, and so we're going to have for this solution big F omega is going to be 1/4. There's the amplitude times by 2 times by a, which is 3, times by sine of omega a, so that's going to be 3 omega divided by omega. We need an a down here as well. Apologies. So you could either write 2a sinc or this could be a and a there. It's up to you how you write. I've done this form down here. Obviously the 3's will cancel out. They don't need to be there. So we've got 2 over 4, so which is 1 over 2. So we have sine of 3 omega divided by 2 omega. Because obviously 2 over 4 is 1 over 2. 2 over 4 is 1 over 2, so you've got 1 over 2. So there's our solution. So all of these ones are applying this formula here, okay? This formula here, okay? This is the key formula for this section. And that's the formula that we derived in the previous lecture. You don't need to know the derivation, but it's useful to see it. Which is why we covered it last week, to know where it's coming from. Okay, and that's the equation to find the Fourier transform. So question 1 was all about applying that equation. Okay. Okay, has everybody got the answers to question 1 now? Please say if you're still writing, I'll take it away. So for question 2, which we'll do next, it's useful to be reminded of the shift properties, which I covered last week, but I'll write them out here just so that we can refer to them. So the time shift property of Fourier transforms. If you've got you're trying to find the Fourier transform of some function that's shifted by distance or time t0 along. So, for example, if you've got a square function or a rectangular function, and instead of it being centered around t equals 0, it's centered around, say, t equals 3 or whatever. t0 will therefore be 3. And to find the Fourier transform, you end up with the same Fourier transform as if it was centered around 0, but it's multiplied by an exponential. And that exponential is e to the minus j omega t0, where that t0 will be the value through which it's shifted. So that's the time shift property, and we'll use that in the first example. But then the other shift property is called the frequency shift property. And so if you're taking the inverse Fourier transform, so f to the minus 1 of some function in omega that is shifted over by omega naught, so we've applied a frequency shift to it, so again it's the same sort of thing. Imagine you had some sort of sinc function or whatever, but instead of it being on omega equals 0, it was on omega equals some other value. Obviously it's shifted by that value. Again, the similar sort of principle applies. You have your time function, so that's as if it was centered on 0, but then it's multiplied by an exponential. And this exponential is e to the j, so it's not minus, it's just j omega naught t, where omega naught is how much you've been shifted over. So these two examples I'm going to go through now apply those principles. And this is example 2. So we have to find the inverse Fourier transform of H omega in part A. H omega. And H omega equals 6 times by sine of 2 omega divided by omega e to the minus 4j omega. Now if we wanted to, we could go through the theory, applying the equation, but we can see straight away that this part here, that's going to be some rectangular function, okay? And we know that with a rectangular function, PA is 2, the Fourier transform of PA is 2 sine omega A divided by omega. So if we were to match these up together, what would A be? Two, okay, so A is 2. But notice that we have a 2 out the front here, and here we've got a 6. So how do we get from 2 to 6? Multiplied by 3, yeah? 2 times 3, you get 6. So we've got an amplitude of 3. So therefore, this Fourier transform for this bit. So let's ignore the. Let's say we had our function. I'll just call it h prime, which is just the bit here, 6 sine 2 omega divided by omega. H prime, in terms of time, is going to be 3 times p 2 t. Okay, so if we just take the rectangular section, or the sinc function here, so we're ignoring this exponential, you do the Fourier transform for this, we get 3p2t, okay? Because obviously this is the theory, the pair that we've got with the sinc function, okay, or the sine over omega a divided by omega. A is 2 and the amplitude must be 3, so we get 3p2t. But notice this exponential is a time shift, okay? We've got something that looks like this being applied to the Fourier transform, to the frequency domain signal. So what's t naught? Looking at this example. 4, exactly. So t naught is 4. And so our inverse Fourier transform of this function is going to be 3 p2 t minus 4. So by applying this bit of theory to this problem and the time shift property to that problem, we end up getting the solution without having to do lots of that integration that we talked about in terms of what the theory says. Just by looking at the pair, we can determine one from the other. Question B gives us another frequency domain signal that looks a bit like this. And we know the Fourier transform, okay, of e to the minus alpha t ut looks similar. We have 1 minus 1 alpha plus j omega. So it looks similar, but there's some significant differences. But knowing this pair, we can solve for this problem. So if we just consider the case, let's ignore this -1 bit. Let's see if we can solve for this problem. Well, this equals, if I divide both sides, if I divide the top and the bottom by 2, I get 1 divided by 1/2 plus j omega. And you can see quite clearly that this is going to be the Fourier transform of that, or the inverse Fourier transform of that. So we've got k omega is going to be e to the minus t divided by 2 ut. Do you all agree? That's k prime. So the inverse Fourier transform of this bit without the frequency shift is going to be an exponential to the power of minus t upon 2 times by the Heaviside step function. Now if we look at the frequency shift property, which is up here at the top, okay, and look at the function that we've got to solve for this one here, can anybody tell me what omega naught would be? You've got some function in the frequency domain, it's omega minus omega naught. Okay, well here we've got a function in the frequency domain with an omega minus an omega naught. Omega naught must therefore be 1, yeah? Well, if you've got this, you find the Fourier transform as if there's no omega naught in there, but then you multiply it by this exponential, e to the j omega naught t. And so to get the inverse Fourier transform of k omega, so yeah, yes. So we're now applying it to this problem, okay. We end up with this solution, e to the minus t upon 2 ut times by e to the minus j t. And obviously we could combine those exponentials together just to make life simpler. T upon, 1/2 plus j times by t u t. So again, we're applying a bit of theory that we know from the previous chapter. So another pair, which is that pair. And we're applying the frequency shift property, which is at the top of the page, to get from this function to the time domain signal version of it. So the inverse Fourier transform. Okay. Let's do question 3. We've got a function g of t there's a value of 1 between tau upon 2 and minus tau upon 2, and it's 0 elsewhere, so quite clearly it's a rectangular function. G, T, T. looks like that. And this question doesn't ask for it, but a question could say, show your work to find the value of the Fourier transform. We've got to find the frequency domain signal of that function. And so I'm actually going to go through the process, although we know automatically what this could possibly be, but let's show it by going through the work. Just to reinforce the idea of what's going on. So applying the equation for the Fourier transform, which is that, okay? It's the integral between minus infinity of infinity of the function multiplied by ej to the minus j omega t, and we're integrating with respect to time. Now obviously it's only non-zero between minus tau upon 2 and tau upon 2, so that's why I'm only integrating between those limits. And the function, the value of the function between those limits is 1, okay? It's just not got a curve, it's just a value of 1. So that's why this looks like it does. And we can obviously integrate this relatively straightforward. This is just e to the minus j omega t, so e to the minus j omega t up here, divided by minus j omega on the bottom, tau upon 2, that's minus, and then we have tau upon 2 up here. And this we apply this limit into here, we've got e to the minus j omega tau upon 2. And then we apply this limit, so that's minus sign there, e to the j omega tau upon 2 divided by minus j omega. Now we know from another clever mathematician type person called Euler that this term can be written as cosine of omega tau divided by 2 minus j sine of omega tau divided by 2. So that's this first exponential. The second exponential, we know again from the same chap, this is cosine omega tau divided by 2 plus j sine omega tau divided by 2, all divided by minus j omega. Obviously this cosine term and this cosine term are the same. There's a minus sign between them. They disappear. We've got a j in this term, a j in this term, and a j on the bottom. They can disappear. And so we end up with equals minus, minus, and minus, and that minus sign disappears, so we end up with 2 sine t omega divided by 2 over omega. For the sake of argument, I'm going to multiply this by tau over tau. So we have 2 tau sine tau omega divided by 2 divided by tau omega. And look, we've got tau omega divided by 2 and tau omega divided by 2. So this is very simply tau sinc tau omega divided by 2.